just keep going, right? So it's my pleasure to introduce our next speaker, Anna. So Anna is a faculty member here at the Martinos Center. She's been developing a lot of tools for high-resolution fMRI, as well as looking at ex vivo data and histology data in the past, and been developing some of these tools, these software tools, laminar analysis. It's really much look. Also, Anna's one of our co-organizers, so thanks, Anna, for all your help. And we'll be talking about visualization of these laminar.
Thank you very much. So yeah, my talk is about visualization, so you can expect a lot of pretty pictures and videos. And as you can see from the title, there's going to be 3 parts of this talk. And I believe strongly that you wouldn't make it the 3rd day of this workshop not knowing what the laminar profile is, but I'm going to tell you anyway. So we're going to start from that. So I want to start with this beautiful histology data. And as you can see here, this is, I believe, myelin stain, and there are these profile lines that were derived by the authors from the gradient field that was computed between PL surface and the gray-white border, as you can see. And then they clustered these profiles, and as you can see here, there were profiles of different kinds that corresponded to different regions of the visual cortex, like V1, V2, and V3. This is a flat version of it. So this is just a nice example showing how you can use profiles as a tools to visualize the, I guess, myeloarchitecture differences between different regions and how you can use them to distinguish between these regions. But let's move on to the MRI world. So now I just want to point out that I'm not trying to argue with Farouk on the laminar versus cortical depth profiles. I do prefer the cortical depth term because it doesn't, we're not trying to refer directly to the anatomical layers. Our resolution is still not quite on that level, but we are talking about depths in terms of percentage of the cortical thickness. So they're on a way relative, right? They're not like distances in millimeters, if that makes sense. So we can talk to Farouk in a coffee break about it. All right, so the cortical depth profiles are used in the cortical depth analysis to study various quantities, and that can be all sorts of different quantities that vary systematically as a function of the cortical depth, including functional signals. So this is our cortex, these are our cortical depth profiles. Now, if we're talking about the functional signals, of course, we assume that our data are co-registered, the functional anatomical data. And there are 2 different ways of creating these profiles. A voxel-based approach, where each fMRI, in this case voxel, would get assigned a cortical depth, and a surface-based approach, where each vertex gets assigned a value, which will be the value of the projected fMRI voxel signal. And just to again refer to Farouk, both of these approaches are compatible with the equivalent sampling if this is something you're interested in using. All right, so let's start with the voxel-based approach. So as I said, each voxel gets assigned depth. So this is again our cortex, and this is our voxel. We're calculating the distances to the nearest white and PL locations, and based on that, we're calculating this depth. And the benefit of this approach is every voxel is counted once because it gets assigned as a unique cortical depth value. And so it's easy to create a profile over a region. You basically just take the voxels, plot them together, and bin them by the depths. Now, what we cannot do here easily, we cannot generate cortical profile at a specific arbitrary location on the cortex, such as a mesh vertex you'll see on the next slide. As you can see here, this profile kind of crosses 2 different voxels, so it's going to be only 2 depths in this specific location. Now, I'm not going to talk a lot about this voxel-based approach because you're going to get hands-on with Renzo in the next block on Laney, which uses this approach. So you're going to learn a lot more, and it's going to be much more practical. But I'm going to talk a little bit more about the surface-based approach, which is used in FreeSurfer, also in different slightly version in Brain Voyager. I'm going to mostly focus on the FreeSurfer version because that's what we use here. So in the FreeSurfer, or in the surface-based approach, we generate first a family of evenly spaced surfaces. So you can see that I have the surfaces now between white matter and PL surface. We usually go for 11 because that gives us 10% spacing between them, so it's kind of nice. And as a next step, we project or interpolate voxels onto the surfaces. So we have this one voxel, and we project it on the surfaces. So we essentially assign the values of these voxels to the surface vertices, okay? So this is cool because it allows us to visualize activation patterns as a function of cortical depth. You can basically go depth by depth and see what's happening. I will show some examples later. It also mimics histology approaches of like physical flattening of the tissue and cutting it. I'll also show the example of that. And it's important to mention that all these meshes have the same topology. So what that means that for each vertex, we can find the corresponding vertex in all the next meshes all the way. So it's relatively easy to just pick one location and create a profile. Now, the downside of this method is that each voxel is counted multiple times because it's projected on multiple surfaces. As you can see, this one example voxel is projected on 2 different surfaces and actually twice on one of them. So if you look at this profile again, it still samples over 2 voxels, right? So just to point it out. It's also possible that if we have very high resolution data, like we're trying and we want to have, we may end up having very high resolution volume to project on the more sparse meshes, and we can omit the voxels. Obviously, we can upsample the surfaces to help to solve this problem, but it's something also to keep in mind. All right, so more on the surface-based approach. So this topological correspondence that I just mentioned kind of comes from the fact that the PL surface is actually made by taking the white matter surface mesh and propagating it towards the gray matter and CSF interface. But the downside of that is that we're ending up with the meshes that have varying vertex density across depths with curvature. So this is a great figure illustrating that. If you look here, we are on the we're on the inside the sulcus on the PL surface, and you can see that the vertex density is really high, versus here when you are looking at the gyres, it's very sparse. And if we project our data on these surfaces, our fMRI data, we'll end up with the curvature-dependent sampling biases. So here's another example of this from my own data set. You can see on the left, we have white matter surface, on the right, PL surface, and these are the histograms. And I used 3 classes like Farouk advised. So we have gyri on the white matter having smallest spacing, so highest density, right? And on the opposite on the PL surface, we have sulci when the spacing when this spacing is smaller. Okay, so this is sort of one of the examples, I guess, of this downside that the voxel grid doesn't really match the surfaces. And so when we're projecting data on the surfaces, we're introducing some smoothing, we're introducing some shifts, distortions maybe is not the best word because it kind of refers to immediately different topics, but I think you know what I mean. And one way to mitigate that is to, again, upsample the surface. Now, obviously, that's not going to solve the problem, but it just can make it a little bit less of a problem. It's going to, surface is going to take more space and computations are going to take longer, but it's something that we can consider here. And another way of trying to address this problem would be to give up the triangular meshes, which are irregular and the distances between neighboring vertices vary, and actually use the meshes as are used in the Brain Voyager, where we have like a grid or lattice and the vertex density is uniform. That's on a way, I mean, maybe that's an extrapolation, but on a way sort of going towards the voxel-based approach. But I'm not a Brain Voyager expert, so you may want to find one to talk about it. All right, and one more thing I want to talk about, and John kind of already talked about it yesterday, but I'm going to talk a little bit more because it's important, is the depth sampling bias. So we have the submillimeter voxels, but they're not still on the level of the acrocortical layers, and we will have 2 to 4 voxels across the cortical depth. So if we take these 2 profiles, they're going to look like stairs, unless we average over more of them. So now one thing to remember here, one important thing to mention is that when we're averaging and pulling over multiple voxels, we do assume that they have similar intensity or activation across layers, okay? So that's something I'm gonna get back to later. And this is sort of a similar kind of just different angle on the same idea, really showing this as a function of the growing ROI. So if we have a smaller ROI, we have less uniform sampling over cortical depths. And as the ROI grows, it becomes more uniform, okay? All right, so now that you haven't seen the examples of the cortical depth profiles, we're gonna show you some more, just because, why not? This is an example where the surface-based analysis is used, but the Brain Voyager one, and the profiles in the visual areas of gradient echo versus spin echo are demonstrated. So it's really just to show you how and what for you can use these profiles as a tool, okay? Here is the next example from another group in our center, from Kaisu, who's sitting there on the back. So this is a surface-based approach, the free surfer one, and they looked at two different cortical regions, auditory cortex and the polymodal cortex, using visual and auditory stimuli. And as you can see here, it's a nice way to look at these profiles, and we can appreciate the difference between the activation in the auditory cortex for these two stimuli and very similar response in the polymodal cortex. And finally, the last example from Renzo's work, voxel-based approach. And I think I've seen this figure at least like 3 times this week, and I'm still counting. A beautiful example of how we can look at the profiles of the activation and use them as a tool to understand and interpret our data and look at the circuits in the connectivity context. All right, so that's all I had to say about the laminar profiles. Now we're going to talk about smoothing. Okay, so the conventional fMRI studies use volume-based smoothing. And why do they do that? Because they want to increase SNR and the same way detection sensitivity. They want to remove across subject variability that helps spatial normalization if they have multiple subjects. And they also may want to remove false positive because the activation is generally assumed to be smooth. But the volume-based smoothing uses these 3D kernels, as you can see here. And on this little example of the cortex, this is, I think, 1.1 millimeter resolution data, and a 3 millimeter full width half max kernel, which is really not that large, okay? And you can see that this kernel is mixing distant voxels from the opposite banks of the sulcus, different tissue types, in this case, CSF and gray matter. When you move it around, white matter will come as well. And potentially also different functional areas depending where we are in the brain. So this can cause activation and mislocalization as it's gonna just get biased away from the side of the neuronal activity. So basically we applied this smoothing to reduce some errors, but we're actually introducing more errors. And this is a really beautiful example of the activation in the working memory paradigm. And you can see we're starting from non-smooth data. That's the one with a lot of dots. And then we're just basically smoothing it all until it becomes one blob. So that's just kind of the illustration what happens, okay? Here is another good one. So this is 0.65 millimeter isotropic data. On the left, we have images are kind of small, but I hope you can see. On the left, we have t-statistic. On the right, we have effect size. And this is the original non-smooth data. You can see activation in visual cortex. And then we start smoothing, 1 millimeter, 2 millimeter, 4 millimeter, 8 millimeter. So what happens? Well, statistical significance goes up, right? You can see that. But what also happens is that the effect size and the spatial accuracy goes drastically down. And at the end, you basically have the activation all over white matter. So I think that should give you an idea why volume smoothing may not be the best choice, especially if you are doing laminar fMRI with, high resolution and small expected regions of activation. So the methods have been proposed to address this problem, such as anatomically informed smoothing, like in this example approach, where the anatomically informed bias functions constrained to cortical ribbon have been applied. So this is a simulated activation in 2 different separate sites. And as they applied constraint smoothing, you can see that on inflated surface, but even in the volume space, these 2 separate sites were preserved. You can see that there is like a gap between them here. It's not like fully gap, but it kind of goes down. It's more like orange. However, once they smooth to the volume-based smoothing, they got one blob with the peak in the middle. So this is very different than what the actual activation was, right? Here's another approach. The task in this example was grasping movements, so expect activation in insula. And as you can see here, with the volume-based smoothing, there's no such thing like activation in insula. And with the surface-based smoothing, which was done along the 2D cortical surface, we can see that there's activation, so the functional activation and localization has been improved, okay? All right, so one more example. Here we have a synthetic bold activations, and we're adding noise to our data. And the top, well, middle row, I guess, is a surface-based methods. The bottom is the volume. So this is zero noise situation, and then we start adding. And what you can see here is that for the surface-based smoothing, we have improved sensitivity, improved spatial accuracy. For the volume-based approach, the activation kind of disappeared, like around 50% of the noise. So these are all good reasons to use surface-based or anatomically informed smoothing. Here is another example from Renzo, how we can use smoothing within the cortical ribbon for visualization. So this is a great example because this is just non-smooth raw data that is included in the paper, but Renzo also included smooth data just to add visualization, because you can actually see these activations much clearer and their laminar shape as well. And here's another part of this figure. Okay, so with this, I just want to talk quickly about our own surface-based smoothing approach that has been mentioned a couple of times, so I kind of felt like I can't really leave it out. So we came up with this approach that sort of works in the surface-based paradigm and uses sub-millimeter voxels that we have now in our fMRI data to look at the cortex as a 3D structure. So we're not only talking about 2D smoothing constrained to the ribbon, but we're trying to do something, just go a step further. So if this is again our cortex, we're taking these small voxels and we kind of redistribute them. So if you look at this data, if you had 3 millimeter voxels, these big white boxes, all the signal in this box will be weighted the same. But you can redistribute this once you have the small voxels, and you can not only change the shape of how this kernel would be placed on the cortex, but you can also weight this contribution of different voxels differently. So we propose this framework that uses, as I said, the family of surface meshes, and we designed these steerable kernels that sort of follow the cortex, but they're also parametrized both in tangential, so laminar, and radial, columnar direction, okay? So you can have this like thin stick kernels, you can have the pancakes kernels, and you can have this intracortical kernels. And first, we just wanted to see if we can come up with a kernel that would help us avoid CSF and white matter to increase sensitivity and tissue specificity. And this intracortical kernels turned out to be the best. You'll see on the next slide, and they're also known as wine corks in the community. Some people still remember. Okay, so we just quickly acquired resting state and breath hold data, and we compared this smoothing approach with the volume-based smoothing, and we found that not only this kernel that skips white matter and CSF outperforms the volume-based smoothing, kind of expect that, but it also outperformed the original lower resolution 3 millimeter data. Similarly, in tissue specificity, functional contrast noise, functional contrast noise ratio. So we concluded that we got the best balance between TSNR and FCNR from this no PL, no white matter intracortical kernel, and it even outperformed the original low resolution data. Okay, but that's all fine and good. But we're here at the laminar fMRI workshop. So what's the message for us from this approach for the laminar analysis? So if we have any prior information about the spatial structure of activation, be it laminar, be it columnar, we can use it and we can smooth our data. Now, we still want to be careful. We don't want to introduce activation that is not there. And I would strongly advise the approach of actually showing the raw data, or at least looking at them before applying any smoothing. One good use case for this that Renzo will be also showing in practice is to actually use the smoothing to create ROI from the separate localizer run, and obviously to aid visualization of your results. Okay, so with this, I'm going to move to the last part, and we're going to talk about the cortical flattening. All right, so the cortical flattening has been around for quite a while, and it started with this raising of sulci and gyri by pencil tracing of the 2D cortex representations based on the outlines from the histology data. So if you see these numbered lines on the left, they correspond to the topo lines on the right. And it's been a great approach used for mapping functional and anatomical cortical areas and their local organization. Going a step further, this approach of flat mounting has been proposed. There we go. And in this approach, what they do, they dissect the cortex from the ex vivo specimen, and they flatten it by hand with 3 cuts, and then they can also fix it, section it, and stain it. So they will get images that you can see on the right of like thin sections of the cortex. So that is really a great tool for studying tangential and columnar organization of the cortex, and has been used for that widely. Oh, I think I crashed the PowerPoint. Oh no, it's back. Okay. Right. So what do you do if your brain is actually still alive in someone's head? So if this, all the development of the MRI and small voxels and approaches to make surfaces from our data, we can actually, instead of flattening the brain itself, flatten the representations of this brain or representations of the surfaces of this brain. So as you can see here in this example from FreeSurfer, this is our inflated hemisphere with cuts, and then we flatten it. And again, I have a video which hopefully plays. Play. Play. I doesn't want to.
It's the laser pointer makes it hard to.
Oh, really? I'm trying to click on it, really.
Yeah, sometimes this happens.
Just like imagine the visualization going from the one on the top to the one on the bottom. That's pretty much what it is, okay? You all have good 3D imagination, right? All right. So, but why do we need or why do we want to use this cortical flattening? So here is a great example how we can much easier see locations and borders of different functional regions. This is an example of the face recognition region specifically. So you can see that on the left in this folded brain, I mean, you can see something, but it's just so much easier for outlining these regions to look at them, even on the inflated hemisphere, but definitely on the flat cortex. And one other sort of subset of experiments where this is a widely used approach or a very helpful, useful approach is experiments that use retinotopy. Just to remind you, the retinotopy is basically a mapping between the neurons that have a receptive field to the visual, between the visual field to the neurons in the visual cortex. So you have this map of the visual field in our cortex. It's slightly distorted because of this magnification variation. But in order to actually see the representation of the visual field in the cortex, you can see that this calcarine sulcus is like very well folded. So what we want to do, we want to actually open it up and flatten it to see our activations better. So if these 2 points here were actually even closer in the original unopened version, they will be flat on this representation. And the retinotopy is widely used. This is just a couple of like more modern examples from the fMRI studies. So it's used as a functional localizer, as you can see here, to delineate different areas boundaries. And it can also be used to design experiments, to design specific types of stimulus, like in John's M paper, or in this work from our study, where we designed the diamond stimulus. So basically, we wanted it to look on the cortical surface like you can see on the left. So we showed the subject what you see on the right, and it works. Okay, so this is also a great example. Remember when I said you can use in the surface depth analysis, you can look over the activation over cortical depth, how it actually looks on the cortex. This is a nice example showing that as well. And the final point I wanted just to show you, obviously you saw it also many times, is a beautiful video that Farouk let me use. And this is a great example how flattening the cortex can help us see this columnar or laminar structures that we're interested in, okay? It's just very pretty, so I'm gonna just end on this. All right, so conclusions. So the laminar or cortical depth profiles, when we are creating them, it's important to remember a couple of things. When we are projecting our data on surfaces, we are interpolating. As I mentioned, we can introduce some special shifts during this process. So it's just important to keep that in mind. And similarly, when we're averaging over multiple profiles within the ROI over multiple voxels, we're also introducing a kind of smoothing. And remember the assumption that all these profiles are supposed to have a similar activation, right? As for smoothing, well, I think I showed you that 3D smoothing is not the best idea if we're looking at this small activations. Anatomically informed or constrained smoothing can be useful to create the ROI from the localizer scan, but also to visualize our data, our results, assuming that we had some prior information about the structure of the activation that we expect. Just one more time, I'm going to reiterate, remember, look at your raw data, show your raw data. It's a great tool, but you have to be careful not to introduce false activations. And the cortical flattening, as you saw, is a great visualization tool, but it can also be useful. I think Daniel might have mentioned that yesterday. If you are debugging things, if you are looking at the segmentation errors or just meshing errors, it's much easier to see it in the inflated version. So it might be helpful for validation on different stages of generating our results as well. And with that, I would like to thank these two gentlemen, especially John, who provided me probably like half of the slides. And also, if anyone's interested, I'm hiring postdocs, so you can scan this and there's a good job done. Thank you.